Lesson 6.5, Logistic Growth. What you'll learn about is how populations grow, the logistic differential equation, and the logistic mathematical growth model. In the previous section, we talked about how populations grow. The rate of change of a population is directly proportional to the size of the population. The differential equation looks something like this. When k is greater than 0, it's a growth model, and it'll yield the mathematical model CE to the KT. And it looks something like this. And this is growth without bound. Now, that's not possible, really, when you talk about food, habitat, and living space, which are constraints to growth. And so this will limit the growth of any real-world population. All right, let's take a look at the logistic differential equation. Here is the growth model we just discussed, and this is a logistic differential equation. Notice it has a factor that is being multiplied to it, and m is what we call the carrying capacity. In the curve, it looks something like this. It's an asymptote that the curve wants to approach. As it gets larger and larger, as t goes to infinity, the population gets closer and closer to m. All right, let's take a look at a problem. What is the carrying capacity for the bears in this wildlife preserve? Well, just looking at the logistic curve model, you can see the answer is 100. And we would like to know when it's growing the fastest. So we want to take the derivative of this growth model and see if we can find its critical point. So let's go ahead and take a look at dp dt. And it's 0.008 p times 100 minus p, and I'm going to distribute, and when I distribute it's going to be 0.8 p take away 0.008 p squared. And again, I want to find the critical point, which means taking the next derivative. This is going to give me 0.8 minus 0.016 p squared. I'm going to set the derivative equal to 0 to figure out the critical points, and that implies that p will be equal to 50. Now let's take a look at the curve right here and see what that means. Remember, logistic growth looks like this. We know the carrying capacity right here is 100, and what we're saying is right here at 50, we're going to find the greatest growing the fastest. Now that means growing the fastest means taking a look at the slope of the tangent line. And you can see the slope of the tangent line does indeed look like it's the steepest at that point. We can check that out by finding the next derivative, and it will be negative 0.16. And since this is a negative number, that tells us that this critical point is indeed a maximum value. All right, let's take a look at another problem. And again, here we have the differential equation that's logistic, and they want us to find the carrying capacity, and it's right here, 1,000. With a calculator, we want to generate a slope field for the differential equation, and over here I have inputted the model right here, and then I have to actually go to program, and I have to use a slope field program, which I've already done. And here is the graph. Here's the slope field. And you can see that it's growing and then it levels off like this. So with a calculator, we have generated the slope field. All right, now the last part, and probably the most difficult, is for us to solve the differential equation. Now, to do that, we're going to have to use separation of variables. We're going to move all the p's to one side, and then we're going to move all the t's to the other side. I'm going to keep this constant here with t's. And then I can go ahead and integrate both sides. I want to remind you that this is going to need partial fractions. We're going to have to take this quotient and divide it into two quotients. So let's go to the next screen, and you can see I've divided it and found my a and my b. I then go ahead and take this constant, bring it outside the integral, and then I'll divide both sides by 1/1000th. And now I have a smaller decimal here, and I've integrated with the natural logs. And then here's my next step. I'm taking the natural logs and I am going to multiply through by -1 because I want this expression first and this expression second. Notice that these are all negative now. And then I'll put the two natural logs together. The difference of the natural logs is the natural log of the quotient. Exponentiate, and then I'll get this expression equal to e to this expression. I'm going to separate these fractions. That'll be 1,000 over p minus 1, which I took 1 to the other side. And now I continue. The 1's over on the other side. I'm going to put my initial condition, and then I'll be able to find e to the -c. That's going to be this 15.398. So now I know what this is, or I should say this. I know what this is. I went ahead and put that in there. And then I'm going to do the reciprocal on this side and do the reciprocal on this side. So all of this will be in the denominator, and then I will cross multiply and take the 1,000 to the other. So this is what the mathematical model looks like. It's a lot different than the mathematical model for exponential growth. Now let's take a look at this general logistic formula. You can see that this is the form we have. At the end, the carrying capacity will be in the numerator. We'll have a 1 plus some kind of constant that we get from the initial condition. And you can see that the coefficient to t is really the product of the carrying capacity and k. Let's go back to the previous problem. When I take this k and I multiply it to m, that's how I get this -0.3. All right, let's talk about some problems that use the logistic equation. So this first one shows us the mathematical model, and it's asking us how many people are infected when the disease is spreading the fastest. And remember, this is going to be that halfway point. So here's the logistic curve. Here's the carrying capacity, m, and this point here where it's growing the fastest is always going to be m². So the answer is 300. Here's another problem that uses the slope field, and they want us to find the differential equation. Well, we can eliminate these because this is actually the mathematical model, not the differential equation. And remember, the differential equation depends on the amount itself. So having any x's involved doesn't make sense. So the only one left is this one that follows that model. And last one, we're being asked to find what the limit of p of t as t approaches infinity. So again, let's go ahead and take a look at the logistic model here. Remember, this is the carrying capacity, m. And so we want to know what happens as t approaches infinity. And so we need to know what m is. And it's kind of difficult here. Let's go ahead and change the way it looks. I am going to get a common denominator of 5,000, which means this will be 10,000 minus p. And then I'm going to take this fraction, move it out of the parentheses, and I'm going to get this. Now it looks more like the logistic differential equation, and I can see this is my carrying capacity, and that's the answer. And this is the end of the screencast.